Okay. In this training video, we're going to look at modeling the triangle group CGP. We're going to do this manually to show you how the modeling process actually works if you're going to do it manually, and also to illustrate that the tools that we have, both the optimization and also the diagnostic displays, show if you're making any mistakes as such during the modeling. So first we open the triangle group CGP, double click on it, and we're greeted in the models display, in my case with two data sets and also a number of models on the right here. If we go to the data sets tab, let's look at what we're actually modeling. We're looking at paired losses as a triangle type. We've got incurred and cumulative forms of it, and they've both got exposure vectors, base exposure associated with them. Alright, now if we go to the, what we're going to do now is actually plot this data. If we go to plots, tab data plots. We've got four tabs here. The first one is unadjusted, so it's just the raw data plotted versus the three directions, so dollar scale. Alright, now I'll just shift these windows around a bit. We've then got adjusted. Now adjusted is adjusted for any inflation vector that we provide, if any. Now in this case we actually haven't created or associated an inflation vector, so we don't actually have any change in these plots. If we then go to normalized, what we do is we divide by the exposure vector that we've associated with the data. So the process is to move from left to right, so raw, inflation adjusted, if any, normalized, adjusting by exposure, and then we take logs, because in PTF we always model on a log scale. Now if you notice the difference between these two graphs is that on the dollar scale we see as the mean's higher, we also get a higher standard deviation of the distribution as well. Whereas if we go to the log scale, the volatility actually looks quite consistent over the whole period. Now that's probably an outlier there, in which case it is just constant volatility. If we open the data sets, just double click on the tab here and double click to open it. This is the data we're actually modeling. Now when we're modeling in a modeling module, be it PTF, MPTF, etc., we always select the data set to model. The reason for that is we're not just interested in the triangle, which happens to be the first tab that's on this display, but also any inflation, premium, or exposure that was associated with the data. And this is where we see that we've actually got exposure associated. We don't have any premiums, they're just set to 1, or we don't have any inflation either, it's just set to 0. Alright, you can also see in this window here that you've got this option for associated triangle. In the case of paid losses, that's the case reserve estimates or incurred loss data. If we had that information, we could associate that triangle, in which case we'd get different summary tables in our forecast summaries when we're actually forecasting from any selected model. Okay, we'll close those windows now. We'll go back to the Models tab and make sure paid loss incremental is selected, which it is. We're now going to left click on the PTF tab to enter into the PTF modeling framework. Do that now. And two windows have now been opened. The weighted residual plot, which you can see just tucked in behind, and the model displays. What we'll do now is we're going to tile vertically, and on the downward arrow we're going to select the option Minimize Regression Tables. And that will tile both the model displays and the residual displays on our right here. Now what we've actually fitted by default is with a parameter in each of the three directions. We've got one development year parameter, we've got one accident year level, and we've got one calendar year parameter. Now this is the starting model that we start with, and from there we can either we can add parameters, delete points, etc. as we go through the modeling process. What we're going to do in this video is going to start with modeling the development year direction, then we're going to model the accident year direction, then calendar. In this example we don't have any heterospecificity. The variation around the development and accident trends are constant. But in the subsequent videos we'll show how to handle that as well when you've got changing volatility. Once we've adjusted for all the trend parameters, we've adjusted for hetero, we would then optimize the model. Once we've done that, we might make further adjustments then At any point during the modeling process, if you decide a point is an outlier, you can remove it. To mark a point as an outlier, let's click on it. For example, this one changes it to be black. We can then see where it is in the other displays. If you change your mind about it, you haven't estimated, just left click it again, it changes back to green. If you did actually mark it as black and estimate it, and then you changed your mind, just right click on the residual display and click Delete Outliers. And it brings it back, and it's marked it as red so that we can see where it is, what points have actually deleted. Just right click on it again to take the mark off, or right click on the display if you've got a number of them and just click Clear Marks. Same thing. Let's look at the development direction on the residual plot. First we maximize the residual plot, click on the title, and what we want to do is add parameters. Parameters are these grey bars. Whenever we see that there's been a change in direction of this central blue line, basically a change in the direction of the way the residuals are behaving. Now what I'm going to do is I'm going to make a number of mistakes doing this deliberately, so that we can see that as we go through the modeling process, if we do make mistakes, we can easily identify them, and the optimization routine will tell us that we didn't need parameters, or in the case of needing parameters, we'd see that from the residuals display straight away. So what I'm going to do first is I'm going to say that this trend between 1 and 2 is the same trend as between 0 and 1. So I'm making a mistake here, and it will become obvious. I'm going to say that the first trend change then is between 2 and 3. To add a trend, we're going to left click, and it will add this grey bar. We haven't actually estimated it yet. All we're doing is marking where we want to add parameters. So I'm saying that this is the same trend. That blue line is the same as that one, but we do have a change of direction in this blue line. It starts going down between 2 and 3. What I'm going to do now is say that there's another trend change between 3 and 4. Now just looking at that by eye, left click to add it, it doesn't look like there's a trend change, and that's in fact what we'll find out when we do the optimization routine. The next thing I'm going to do is add a trend between 4 and 5. Alright, I'm not going to add any changes after this, partly because we don't have that many points. We're starting to get only 4 and 3 observations down here to actually estimate those trends. So I'm going to say I'm just going to smooth them and just take out this 4 and 5 as the last parameter I can estimate. Now, to estimate this model, click on the lightning bolt with a blue E beside it. See that? Now we see that we've actually estimated this model. We've now fitted these parameters, and we find that between 0 and 1 is very different between 1 and 2. So if we'd made that mistake and said it was the same, once we'd estimated, we'd find that no, it is actually quite different, and it would be obvious that we needed to add a parameter there. Let's do that now by left clicking between 1 and 2 and clicking Estimate again. Okay. Now looking at this display, we find that this point in development period 7 is sitting at 3.5 is quite different to the other points. Let's check whether that's an outlier by clicking on the diagnostic tools. It's the hourglass with the 3 diamonds up here at the top. Open that. And looking at the normality plot, we see this point, which if you point your mouse over it, will come up with a toolbar of where it is, and it's development period 7. It's that same point I pointed out in development. It's quite different from the rest of the displays. We can also see it in the Outliers tab. If you've got more than one of them, you can see which points are where in this table. To move it as an outlier, just left click on it. It changes it to black using my settings. Estimate. Okay. If you go back to diagnostic plots, it's now looking quite reasonable. We'll go back to the residual displays. Okay. We're now going to look at it by accident year. So click on the title bar for development. Click on the accident year title bar just to look at that. Okay. Now what I'm going to do here is I'm going to at least pretend that the accident level between 73 and 74 is lower than the other accident years, which it's possible. Okay, because we're saying that this is relatively higher, then it drops down for a bit, and then goes up again. So let's actually test that. To add a parameter in the accident year direction, you do actually need to right click. If you left click, it will add this D parameter. You don't actually want a D, you want an L. So either left click all the way up to get an L, or right click in the first place just to get the L straight away. Okay, the difference between the D's, 1, 2, etc. up to L will be explained in a subsequent video. So now we'll estimate that. And now we see that these points that we thought were a little bit lower have now been moved up, so we're actually adjusting downwards. Okay, click on that title. Now that we've done development and accident, let's now look at calendar. Again, click on the title bar to maximize it. What we see is after from 75 onwards, it actually looks quite flat, but there seems to be this dip here between 72 and 75. We're going down to 74 and then up again. So let's fit that by adding a trend between 72 and 73. You can left click on these ones. 74 and 75, I'll say that this trend is the same, between 75 and 76, so that we say it goes up and then flat. Now we're not adding trend changes here because we've only got a few observations. So the same principle as with development trend in the tail. The title, estimate, and now we're going to look at the model display. So click on this blue squiggly line up here, and the title vertically minimizing regression tables so that we can see them side by side. I'll get rid of the diagnostics display as well so we can see it clearly. Just minimize it if you had it open. And again, tile vertically. Now this is the model that's actually been fitted to this data, and we can see a lot of colors on it. We'll now save it. So to save it, click on this pink M with this downward arrow going into the database, and either type a name or I'm going to call it before optimize. So I'm just going to overwrite that model. Yes. Now, what we're going to do now is we can see all these colors on the display, and what that actually means is that the model we've fitted is not the most statistically optimal. So what we're going to do is step through the optimization routine to find out exactly how it's going to remove parameters or otherwise adjust them. So the first thing that the optimization routine is going to do is going to remove anything that's got a pink bar next to it. So looking at the model display, the first thing it's going to do is remove that parameter between 3 and 4 and say it's actually the same between 2 and 3. And then we'll re-estimate this parameter as being from period 2 to 4. Let's do that now. Okay. Now looking at the model display, we can see we've got something else that's pink. So now we know that it's going to remove this accident year parameter. Do that. Now it's re-estimated it, and now it's got another pink line, it's got this other accident year parameter, and saying, well, we didn't actually have that drop between 73 and 74, it's actually just variation, and it wasn't actually a drop there. Now, the next thing it's actually going to do is that it's actually going to put a constraint in. Now we're going to cover constraints in another video, so I won't actually talk about them there, we'll just click on the single row. It adds that constraint, that's what this horizontal line means. Now we can see we've got these red and blue lines here. Now the red line just means that it's not significantly different from 0, which means if we optimize it's going to set that parameter to be 0 exactly, which is in fact what happens. Now after making these adjustments to the accident year level, we then find that we can make an adjustment in the development year direction and find that this parameter, which we previously estimated being going up, is in fact 0. Let's optimize now and we'll set that. Now there's no further colors in the display, so if we can continue clicking that O button, nothing is actually happening. We'll now save this model. We'll call it good. Okay. Now if we wanted to do that whole process in one step, we could have just used this double O button. So that double O would have done every single O step, but just presented us with one result. So if we go just to illustrate that, I'm going to load the model before optimize, and just click on the double O, and we end up with a good model that we'd saved, but just with one click of the button. Okay. Notice also we've got the triangle group name up in the window, we've got the dataset name that we're looking at, we've got the modeling module, in this case PTF, we've also got the name of the model that was last saved, or last loaded. So in this case I've loaded before optimized to do the double O again, and this question mark just indicates that the model has been changed since we last saved. So I optimized it is different from the before optimized model. Let's now load the model good. Okay, and now you notice that question mark has disappeared. Now the next thing we're going to look at is just the normality of it. So when we're doing the regression model, we're making an assumption that the normality of the error term is reasonable. Let's test that assumption now by clicking on this hourglass with the green diamonds. We looked at it before. We just stretch the window out. And what we see is for the residuals, we're finding that we do actually, the assumption of normality can't be rejected. So if in fact we'd actually found that the p-value of this test was less than, say, 0.05, we could reject the null hypothesis at 5%. Similarly, if it was less than 0.1, we could reject it at 10%. In this case, the p-value is greater than 0.5, and we won't reject the null hypothesis. So our assumption of normality has been satisfied. We'll close that now. The next thing we're going to look at is the auto-validation. This is under this green trapezoid here with the blue AV. Click on that. Then we're going to step back 4 periods. So just on a downward arrow, go back 4 periods to 1976. Now, we'll do that now. Right, so what we're doing is stepping back in time at previous year end. So we've got the data 79, so that's doing no validation. If we remove the calendar year 79, we step back to 78. And we're looking at saying, okay, given our currently identified model structure, how do the parameters change having removed that 79 year, and what's the distribution of the forecast at year end 79? So in other words, after 1979. It's similarly with stepping back in time to 1976. And what we find is that given this model structure, including that zero parameter assumption, and the structure of development and actions here, the reserves are actually extremely stable. The mean reserve is saying roughly 13 million, and a standard deviation is saying around about 1 million. So if we look at the forecast, we can see that graphically. All those are quite well centered around this final estimate at 1979. And if we look at the logbook, we can see how the parameters are changing, and we find that for the gamma direction, which is your key direction, it's the development, and we find that this trend is if I just maximize that, we can see it is minus 0.6807, plus or minus 3.86%. That doesn't change very much as we remove the calendar year, so it's minus 0.68, as we mentioned, minus 0.7, minus 0.65, etc. Obviously, the standard deviation of this parameter is going up because we're removing observations as we're stepping back. Similarly, the alpha parameters are not changing very much. 6.583 was the last level parameter, and as we step back, it's saying roughly about that same region. The standard deviation is changing a little bit as well. If we look at the observations that we're excluding, this is under the prediction areas residuals tab. Just click that now. It's got a number of sub-tabs on it, but what we're interested in is each validation period, but what we're going to look at is 1979 to 1976, so let's click that there now. And what we're looking in this graph is the graph displays the prediction areas versus development here. In other words, these are the points that we've excluded by the 4 years that we've removed, and this is where the residuals actually lie based on that new fitted model using the structure that we'd identified. And the residuals actually look quite good. There's no obvious pattern there, similarly with accident and calendar. If we look at the normality of these residuals, so we're projecting normal distributions, so we expect that if our model is doing well and the assumption of normality is reasonable, then we expect to see that our points that we're excluding, that we're now projecting now, should follow a normal distribution if that assumption was reasonable. And in fact it actually does. You can see again the p-value is greater than 0.5. Now we're projecting 34 observations, and to do that we're actually using only 28 observations. And the reason that we can do this so successfully is because of the trend structure being so stable that we're set back through the calendar years. Alright, and some models you actually won't be able to perform validation. So for example, if you actually had a trend change between the last year, for instance, you wouldn't be able to step back in time because you wouldn't be able to estimate this trend change when you placed it in. But in cases where you do actually have a stable structure, like this example, auto-validation actually works very well, and if it steps back through to 1976, we'll just estimate and we open that table again. So if we were at the end of 1976, we actually would have done a very good job of estimating the reserve at year-end 1979, and done an excellent job of projecting those intermediate years. Right, that actually concludes this video on CDP, and we're going to look at CDP in further detail in the subsequent video and other modeling. Thank you.